Hi everyone, welcome to Chapter 7. In Chapter 7, we're going to change gears a little bit. So in Chapter 7, we're going to start taking a look at the idea of probability, which we're going to stay with for the rest of the semester. All the way through 7, 8, 9, and then that little bit of 18 that we do at the end of the semester. It's all going to be about probability. But before we can begin probability, we have to do what we always do at the beginning of any chapter or any section. We're going to take a look at some terminology and some underlying mathematical concepts that'll be the basis of it. So section 7.1 is going to be about sets. We have a couple objectives here. That's to take a look at the terms and the definitions of those terms we're going to use, and then we're going to take a look at some operations on sets. That'd be like the math of the sets. We'll start out with our terminology. First off, what is a set? Well, the mathematical definition says that a set is a collection of objects whose contents can be clearly determined. We'll circle back to that and talk about what that means, but that clearly determined becomes a little bit tricky depending on what your set is. Right? The objects in the set, the things that are in the set, we call those the elements of the set or the members of the set. For whatever reason, I tend to prefer to use the word element, but you can use the word members. A set must be well defined, and this goes back to that clearly determined, meaning that its contents can be clearly determined. Now, we should assume then that it is the reader of the set that we're worried about. That is the person who's reading the mathematics. We need to make sure that they understand what's in the set. If you know what's in it, that doesn't mean that everybody knows what's in it. So we'll take a look at this from the reader's perspective. Now, there is no way to write a set necessarily for every situation where every single person would understand exactly what's in the set. So we're going to go with should an average person or should the average person who reads this know this, then it's well defined, right? And the last thing we have here is that the order that the elements appear when they're listed in the set is unimportant to the set. And what that means is if I have two elements in the set, that the order that I put them in there is irrelevant, right? All right, so some more stuff about sets. The methods that we have at hand for representing sets, there are three of them. There's the roster method, the set builder notation, and then just plain old words. Right? Each of these has its pluses and minuses, and we'll take a look at them. Right? All right, so what I'd like to do is I would like to take a look at the set that represents the days of the week, and I will represent it in all three of these ways. Right? We're going to start out by representing it using what's called the roster method. Now, the first thing I'm going to do is I'm going to give my set a name. Now, in set theory, we almost always use capital letters to define a set or to give a name to a set. So I'm just going to call this set A. And I'm going to say that set A is equal to, and then I use these braces. And then inside of these braces, what I'm going to do is in here is I'm going to place the elements of the set. So the days of the week, we've got Monday. And then I'm going to use a comma. And then Tuesday. And then a comma, and those commas separate the elements of the set. Wednesday, comma, Thursday, Friday, I'm going to run out of space here, aren't I? Saturday, and Sunday. And then I close off the set on the other end by using these braces. And so I just want to highlight some important aspects of this real quick, okay? The brace here and the brace here, that's what tells me where the set starts and where the set stops. The name over there tells me what this set's name is, and then the commas separate the elements of the set. And so when I look at this, I would say that there are 1, 2, 3, 4, 5, 6, 7. Now I'm going to go back to the definitions and say, okay, do I meet all of the definitions for a set? That is, do I have a collection of objects whose contents can be clearly determined? Yep, I've got a set, braces in the front end, braces in the back end, elements listed with commas in the middle, right? Is it well defined? Right? So if someone read that, would they know that I'm talking about the days of the week? Right? And then the last one says that the order of the elements that I put in there is unimportant. So I started with Monday and went through Sunday. If you started through Sunday and went through Saturday, would that be the same set? Okay. Set builder notation is a different way to describe sets. Remember, we're taking a look at the exact same set, but we're going to represent it 3 different ways. This was the roster method. The roster method is great. It lists things out. It's real easy to read, right? Set builder is a slightly more formal mathematical notation. You've probably seen set builder before in your math class. So we would say that set A is the set of all x's such that x is a day of the week. And there I've got my set builder notation. Set builder notation is broken up into 3 things, really. You've got the braces on the front end, the braces on the back end to tell you that it's a set. You have a variable over here that defines the variable of the set, and then we have conditions over here on the right that make that variable true. Now, this is not an ideal set to be representing using set builder notation. You might have seen this before in a math class where you maybe saw something like this. And so this would represent the set of all x's. The set, and why is it a set? It's a set because of that and that. The set of all x's, where x is an even number and it's bigger than 5. So that would be 6, 8, 10, 12, 14, and so on and so forth. Okay, so set builder notation, just a different way to represent a set. And then words. Well, words for the set containing the days of the week would be the set of the days of the week. Just literally using words, right? Now, to meet the requirements, that is, to meet the requirements of a set to be clearly defined or well-defined, roster method is great, right? Set builder notation is good and can be great depending on the reader, because some people are more comfortable reading this. Words are our weakest, because what one person thinks is clear, another person might think isn't too clear. Now, that's not to say that words aren't good, because sometimes words are the only way to describe a set. Right? Every single one of these has its limitations. Roster method is limited because you actually have to list all the elements. And if I had a set that had 1,000 things in it, I don't want to write them all out. I'd want a more convenient way to write those things than having to write 1,000 things separated by commas. Right? Set builder notation is really good, but set builder notation has its own limitation. The limitation for set builder notation is it really is a formal mathematical language. It's a formal notation, and if someone isn't comfortable reading it, it can get pretty ugly. Like, what if I wrote some set builder notation that looked like this mess? What if I said C is the set of all x's such that and what the heck does that even mean? To say that, what does this mean? And what does that mean to say x is abundant? Well, I mean, that's where we get into this definition right here. Who's the reader? Who's the person who's reading this, and would they be expected to understand that notation? Now, there are math classes out there for which this would be an expectation, and that you should be able to read that and understand it. This is not one of those math classes. Okay? So, well-defined is a slippery definition, because I don't know what well-defined is, but I know when something isn't well-defined, that's for certain. All right. Let's start taking a look at some set operations. So the set operations we're going to look at, we're going to look at the element notation and the subset notation. Okay. All right, so this first notation right here is our element notation. This is the notation that tells me that something is in an element of a greater set. So for example, I could say this: Monday is an element of set A. Because as we defined set A up here, A being a day of the week, Monday is an element of that week or of that set. I could also say Tuesday is an element of set A, because if you went and found set A wherever it, don't want that. If you went and found set A and looked inside of it, you would see Tuesday. Now, as with everything else in mathematics, if we put a line through something, it means it's not. So if I said this, dog is not an element of set A, meaning that if you go find set A and look inside of it, will you see the word dog? So that is our element notation. We also have subset notation. Okay? Now the mathematical definition says that set A is a subset of set B if every element in set A is also an element in set B. Now what I'm going to do is I'm going to make up a simpler example than the one before so we can work on this. I'm going to redefine it, and I'm going to say that set A is the set 2, 4, 6, 8, 10. And I'm going to say the set B is the set 4, 10. Okay? And now my question is B a subset of set A? Right? So this is kind of like inequality notation, right? We're saying that the one on the left is a subset of the one on the right, right? Or more importantly, we are saying that the elements of set B are also elements of set A. Okay? So when I look at set B, B is 4 and 10. Are 4 and 10 also elements of set A? Well, there's the 10, there's the 4, so yeah, B is a subset of set A. Right. But over here in the subset notation, I have two different symbols. I have this one, and then I've got the other one. I've got this one. This one still has a B on the left. This one still has an A on the right, but now it's got a different symbol in the middle, right? And that symbol in the middle is the proper subset notation, or proper subset symbol. And basically what that proper subset symbol says is it says that B is a subset of A, and B is also smaller in size than set A, meaning that there are elements in A that are not elements of B. Think of it like this. What's the difference between saying x is less than or equal to 3 and saying that x is less than 3? Do you see how this first one implies that there could be equality, but the second one says that they can't be equal, it has to be just smaller than 3? Okay? That first notation is smaller or equal, and the second one is just smaller. Same idea here. This first one up top, a subset notation, because of that line under it, gives the possibility that B and A could be the same set. They could be equal sets, and that wouldn't violate the rule. Just like we could say that 3 is less than or equal to 3. Right? The second one, the proper subset notation, says that B has to be smaller than set A. There has to be elements in A that are not in B. Okay? All right, let's take a look at some examples over here. Our job for these should be easy because all we have to do is write true or false for each of these statements. So number 1 over here, is that a true statement or a false statement? Well, the left-hand side has the number 3, and then I've got the element symbol, and the right-hand side has the set 2, 5, 7, and 8. So is 3 an element of the set 2, 5, 7, 9, 10? And I don't see a 3 in there anywhere, so that would be a false statement. How about number 2? Is 6 an element of -2, 6, 9, 5? And it looks like there is a 6 in there. It's right there. So that means that we're looking at a true statement. Number 9 here. I'm sorry, number 9. Number 3 here is 9 not an element of the set 2, 1, 5, 8. Well, slash line through it means it's not in there. So is 9 not in there? 9 is definitely not in there. So that would be a true statement. Number 4, 3 not in there? Yep, that's true. Number 5, are those two sets equal? Let's see, the one on the left has the elements 2, 5, 8, and 9. The one on the right has the elements 2, 5, 9, and 8. But the definition of set said that the order doesn't matter. So the fact that the one on the left says 8, then 9, the one on the right says 9 and 8 doesn't matter. So yeah, that is a true statement. Those two sets are equal. Okay. How about number 6 here? Are those two sets equal? Well, let's check and see. I got a 3 here, a 3 here, a 7 here, a 7 here, a 12 here, a 12 here, a 14 here, a 14 here. I got a 0 here that is not there. So then those two sets aren't equal because there is an element in the one on the left that is not in the one on the right. Right? Number 7. All whole numbers greater than 7 and less than 10, 8 and 9. Are those two sets the same? Are they equal? Now I will tell you that this is a trick question because the answer is false. Right? And here's why. Braces here, braces here means that that is a set. There's no set builder notation. There's none of this X such that business there. So that means that this is a set that is being defined using roster method. Do you see any commas? And since there are no commas in this, there are no commas anywhere, this whole phrase here is simply one element. And that element is definitely not the number 8, nor is it the number 9. Right? Now let's take a look at number 8, which has been done correctly. Number 8 says on the left, I've got a set builder notation defined set where it's all of the x's such that x is an odd integer between 6 and 18. So what are the odd integers between 6 and 18? Well, that's going to be 7, 9, 11, 13, 15, and 17. Is that the same as this? I don't think it is, because what's here but not there? So this is also a false statement. I'm going to skip 9 and 10. Don't worry about those. Okay. All right. Element of, not an element of, equal to, not equal to. Last thing we'll do is we'll take a look at 11 through 16 here. We have some sets defined for us. Set A using roster method is 2, 4, 6, 10, 12. Set B, 2, 4, 8, 10. Set C, 4, 8, 12. D is 2 and 10. E is 6. And U is 2, 4, 6, 8, 10, 12, 14. And our job is to insert either the subset or not a subset symbol to make each statement true. So starting here with number 11. A, U. A is 2, 4, 6, 10, 12. U is 2, 4, 6, 8, 10, 12, 14. I see that as a subset because every element in the set on the left, 2, 4, 6, 10, 12, is also an element of the set on the right, 2, 4, 6, 8, 10, 12, 14. All right, how about number 12? E is 6, A is 2, 4, 6, 10, 12. There's a 6 here, there's a 6. Yep, subset. Okay. How about number 13? Well, sometimes I'll have people say they want to do this to make it a true statement. Now, I've searched and searched and searched, and I can find nowhere online, no reputable source that tells me that this is wrong. But I've never seen anyone do it. As far as I know, these two symbols are only allowed to be used in that orientation. That is, the element on the left must be a subset of the element on the right. Now, I can't verify this. I can't find any source other than me that says this is true. So I'm going to go with this. Right? Number 14, B and C. Well, B is 2, 4, 8, 10. C is 4, 8, 12. Well, the 4 and the 8 match, but there's a 2 and a 10 over here, and that's not a subset. Right? All right, what's going on here in number 15? What's that thing? Well, this thing is what's called the empty set. It is the symbol that we use to say that this is a set that contains absolutely nothing. You can also do this. Oops. Where you just use braces on both ends and you put nothing in the middle. And the fact that there is nothing in between those two braces says that this is a set that contains no elements. Okay? All right, so now's the question at hand. Is the empty set a subset of set A or not a subset of set A? Well, here's the answer. It's a subset. Now you might be wondering, how can that be true? Well, it's the way that math works. And what math says is, unless you violate the rule, you have followed the rule. And so the reason that things are not subsets, like over here in number 14, is because there are numbers in the set on the left that are not present in the set on the right. That's when you violated the rule. So is there anything here that isn't also in there? And here comes the double negative. Since there's nothing on the left that is not in the set on the right, it didn't violate the rule. And if you didn't violate the rule, you followed the rule and you are a subset. All right. Last one, and then we'll call it a video. 0, 2, and D. D is the set 2, 10. There's the 2, but is there a 0 in D? So then we would say that it is not a subset. All right. We'll come back with part 2 and start here at more set operations. Have a good one.